morning everyone. Today I am going to present OS operating system concept assignment, which is design and evolution of CPU scheduling algorithms. Let us see introduction. Operating system scheduling. CPU scheduling is a fundamental function of an operating system that determines which process will use the CPU next. Since multiple processes often compete for a single process CPU, the scheduler improves system performance by reducing waiting time, maximizing CPU utilization, improving throughput, and providing fairness among processors. Scheduling ensures efficient process execution and enhances overall responsive of the system. Next we will see overview of the chosen scheduling algorithm. Shortest job. First is a non-primitive scheduling algorithm in which the processor with the smallest CPU burst time is selected next for execution. So next key features are minimizes average waiting time and turnaround time, favors short processes, simple to implement, and major drawbacks is long processes may suffer starvation if several short job keeps arriving. To overcome starvation, we extend ASJP with an aging optimization technique, which dynamically reduces the effective burst time of long waiting processes so they eventually get scheduled. Objectives of the assignment is design a non-primitive SJP CPU scheduling model and implement the algorithm using Python and evaluate performance matrices including waiting time, turnaround time, response time, and context switches and CPU utilization. Optimize the algorithm using aging to reduce starvation of long processor and present a Gantt charts and tables and observations. Experimental setup. Coming to programming language, we use Python and tools and Python ideally or Jupyter notebook, and there is 3 data sets, which first data set purpose is to basic validation of correct functioning, and second data set purpose is to demonstrate SJP starvation aging optimization, and third dataset checks behavior with gaps, mixed burst, late arriving, short jobs. So coming to implementation steps, first we have to define process structure and input the dataset. Next, detect CPU bound versus input output bound processes and initialize ready queue and simulation clock. At each scheduling decision, select processors that have arrived and compute effective bursts. Choose the process with the smallest effective burst and execute processes non-preemptively until completions. Update matrices and next store Gantt chart segments and compute averages and CPU utilization, and repeat for base SGP and SGF plus aging. Next, at last, compare results across datasets. So this is the flowcharts and the complete code which is in Python. We'll get the output as first we will put input, enter number of process 4 and enter arrival time and bus time. We have given arrival time and bus time, and it generated Gantt charts this and process table and with also comparison table. So associated Gantt charts are P1 runs from 0 to 8 at time 0. Only P1 has arrived, shortest job among arrived processes. P2 runs from 8 to 12 at time 8. Processes P1, P3, P4, P2, P3, P4 are waiting. Bus time P2 is equals to P4, P3 is equals to 9, P5, P4 is equals to 5. So among these, P2 is a shortest, so selected. P4 runs from 12 to 17. Remaining P3 and P4, which is P3 is equals to 9, P4 is equals to 5. Shortest burst among arrived is P4. So that is they selected. P3 runs from 17 to 26. Only processors left from P3 exits last. This is observation which we get waiting time, turnaround time, rest time, and number of context switches. And waiting time, we will get average waiting time is equals to 7.75. Observation, we will see the shortest job executes earlier, leading to low waiting times for P1 and P2. Longer processors such as P3 experience higher waiting time due to SGS tendency to postpone long process. Coming to turnaround time, shortest processors show lower turnaround time due to early scheduling. P3 has the highest turnaround time because it waits for all shortest jobs to finish. Response time follows the same pattern as waiting time since processors are not preempted. Larger burst processors consistently face higher response time. Coming to number of context switches. Context switch occurs whenever CPU changes from one process to another. Sequence is P1, P2, P4, P3 is equal to 3. 3 context switches. Observation, non-preemptive algorithms usually have a low number of context switches and run overhead and improve CPU efficiency. Thank you.